Dr. Jeff. So Jeff is lead developer of the open source BlastFoam computational fluid dynamic solver, which is developed by Synthetik applied technologies, where he was worked since 2019. So it's over 3 years. And Jeff received his PhD in mechanical engineering from Iowa State University in MS, IA, and he focused on conjecture-based momentum methods and other standard Euclidean methods for simulating multi-phase flows. And his works are funded and endorsed by the US Department of Defense for blast load prediction and have a global community of users. And he leads in the disciplinary science and engineering software development projects with emphasis in the fields of detonation, thermodynamics, fluid dynamics, energetic materials, and structural materials, and heat transfer. And most recently, Jeff has led several US government-funded projects, including modeling and simulation for the super heavy improvised explosive loading demonstration test program, and the development of modeling and simulation tools for propellants design and optimization for the US Army. So let's welcome Jeff. So Jeff, the time is yours.
All right. Good morning, or I guess night for wherever you are. So I'm Jeff Heylmun, and today I'm going to be talking about our BlastFoam library, which is really a toolbox for really highly compressible flows. Specifically, we'll be talking about explosives today. Okay, so just a little bit of overview of what we're going to be talking about. So we'll just go over BlastFoam briefly, kind of the background of it and what exactly it is. Talk about the governing equations specific to blast, kind of the standard blast problem. And then we'll go through the equations of state that we use and some simple detonation models. And then we'll just briefly go through some of our validation cases. So starting with the Kingry-Bulmash, which is kind of a simplified equation set for quickly predicting blast loads. Next, we'll move on to rate sticks, which we'll be looking at some more of the complex activation models. And then finally, we have the Pendyne case, or what we refer to as the Pendyne case, which is shockwave interactions with obstacles. Okay, so a little bit about us. So BlastFoam is developed by Synthetik Applied Technologies. We were founded in 2017. Currently, we're based out of the Capital Factory in Austin, Texas. So we're located with a bunch of other government clients as well as other integrators. And really what we do is we develop and maintain state-of-the-art software platforms. So this includes BlastFoam, and then it also includes kind of derivatives of that, including iBallistics and Citicore, which both make use of BlastFoam, but also extend it. We do a lot of work with both commercial and federal clients and do applied research projects. That's really what we do. So I'm Jeff Heylmun. I got my PhD in mechanical engineering from Iowa State University under Alberto Pasalacqua and Dr. Rodney Fox. And I have been the lead developer of the BlastFoam CFD library, toolbox, solver, whatever you want to call it. And really what my focus has been on, it's been on extending OpenFOAM for explicit solvers, really focusing on multi-phase and specifically a very compressible multi-phase. Next, we have Dr. Ben Shields. Dr. Ben Shields graduated with his PhD from University of Illinois, Urbana-Champaign. And he really does a lot of our running for kind of the cityscape calculations, which I'll show in a little bit. Next, we have Peter Vonk. Peter Vonk did the initial implementation of BlastFoam, actually, so kind of the proof of concept, but he also leads a lot of our R&D efforts, as well as develops some of his own scientific computing software. And then lastly, we have Tim Brewer. So Tim Brewer was a technical Army officer. He has a ton of experience in modeling and simulation. And if you send us an email, you'll probably talk to Tim. He also does a lot of our cases as well as really cool visuals. Okay, so just some quick examples. So top, we have it's kind of a more complex geometry. So looking at loading over blast walls, going down first. So we have a cityscape geometry. These are pretty standard for us. We run a lot of these. I'll have a video on the next slide. Next, we have some Taylor-Richtmeier instabilities. So looking at those instabilities that form due to density gradients, basically the outer edge of a charge. Next, particle and dust entrainment. So this is more of opposed to kind of the VOF shared velocity kind of approach to multi-phase. This is a more standard Euler method where you have drag and heat transfer and things like that. Next, we have nuclear weapon effects. So we've done a little bit of work looking at some of those extremely high energy situations. Done a little bit of work with UNDEX. We'll be moving on to that more so. So underwater detonations, delayed multi-strikes, Lagrangian particles, and then structural responses and interactions, which is a lot of what we do actually. There we go. All right, so these are those instabilities. So this is a quasi DNS. It's more of just an example. But you can see those instabilities forming on the surface there. Next, we have that loading over a blast wall, looking at non-standard geometries or non-structured geometries. The bottom two are more illustrative of what the kind of cases we typically run. So on the left, we have loading on a structure. So this was actually done as part of called the shield test. I believe it was 12.5 tons of ANFO was detonated in a field in Norway. And basically, we wanted to see what the government wanted to see what the structural response was. So we ran these air blast calculations, and then we provided the outputs of the loading on that to another group who actually looked at the response of the structure. And then lastly, we have our cityscape calculations. So these are pretty standard for us. So basically, we're looking for damage, loading, that kind of stuff on buildings to see the kind of damage that would occur if something were to happen. Okay, so why does BlastFoam exist? As you can imagine, this kind of field is fairly restricted. So there aren't really any other unrestricted free or open source codes that you can really get. So a lot of commercial codes, if they do offer the kind of functionality that we need, it's often very restrictive or it's very expensive. A lot of times there's certain things that are missing that basically don't allow you to run certain classes of problems. So really the purpose of BlastFoam was to kind of fill in this gap and provide something that would allow people to run these kind of problems and learn the physics behind these kinds of problems without having to pay tons of money for commercial codes. So obviously we use OpenFOAM. It's exactly what we wanted. Basically, it's a great base to start everything off with. It has all of the finite volume schemes. It's easily extensible for both the finite volume schemes and the physics. It has parallel right out of the box. It has mesh generation, mesh conversion, all that good stuff. It has tons of utilities, which we make heavy use of. Really, it's just a nice balance of usability, scalability, performance, and then easily extendable. We don't have to re-implement all the turbulence models. They're just there. Yeah, just a lot of stuff that we didn't have to do, and we could focus on what we actually needed, being the very compressible physics or slightly different numerics. Okay, so where has BlastFoam been and where are we going? So BlastFoam was originally presented back in 2016, 2017 at the OpenFOAM Users Conference. So this was the work done by Peter Vonk. This was kind of it was basically a modified row central foam with some different equation estates. And then I came on in October of 2019, and we had our first public release of BlastFoam in November 2019. And then since then, we've had a bunch of releases, basically adding new stuff, improving radiation, different equation states, further integration with other OpenFOAM models such as turbulence. We've done a fair amount of work with adaptive mesh refinement, primarily porting from Rettmeyer 2019. So this includes things like 2D and 2D axisymmetric adaptive mesh refinement with load balancing. Some more of that Euler type two-phase models or multi-phase models. And then more recently, we've been getting into fluid structure interaction and some coupling to other external codes. So previously we had support for precise. In our upcoming release, which will be August 25th, I think, we'll have support for solids for foam. So both being able to couple externally to solids for foam. And then also we'll have our own kind of modified version of that, which you can just use directly. In the upcoming release, we'll also have, so the numerics library, which is newish, has some things like numerical integration, root finding, minimization, all that kind of stuff. And then we've also added burst patches and then polyhedral refinement from Foam Extend. Okay, so now more onto the actual blast stuff. So just a quick overview of the governing equations. So these are going to be specific to what we consider the standard detonation problem. So you can obviously do multiple charges, multiple species or explosive types. But kind of the standard problem is we have one charge and it's surrounded in air. And that's kind of the class of problems we're going to be talking about. So here we have our governing equations. So U is going to be our conservative variables. So we have volume fraction. We have our two phase masses. And then we have momentum and total energy. So it's basically the standard Euler equations. We just have our density split over two terms or two phases. Really the only difference here is that we have in our volume fraction transport, we have our non-conservative term, and then we also have this energy source. So this energy source is due to detonations. I'll talk a little bit about that. That's kind of what the detonation models are. So this is typically considered the 5-equation model. We're specifically using the one from Shang 2011. So this actually uses the Migron-Eisen form of the equation estate, and that's how they do their blending, if you will, of pressure and speed of sound and other variables, using the gamma term to correctly weight those values. So we have a single shared velocity and temperature or energy, but we do have unique phase masses. So that means that like the TNT has its own density and the air has its own density. And we have some volume fraction of each. We only transport one volume fraction, kind of standard to two phase. And then for our actual advection, we use Riemann solvers, and we have ODE time integration for our hyperbolic fluxes. And then we also have, again, that additional source term for energy added due to detonations. Okay, so the main difference in these problems compared to like a more standard compressible VOF simulation is really going to be the equation of state. So I'll talk about that in a second. First, we'll just kind of go over the model problem. So basically what we do is we assume that we have some solid mass of explosive product or reactants here, call them reactants. And those reactants are initiated at some point. And basically from that point, we have a wave that propagates outwards. And as the wave passes the material, it reacts and becomes the products. So we assume it's basically instantaneous. But this wave moves at some prescribed detonation velocity. And these are actually surprisingly easy to find for most materials. It's basically the speed of sound through a solid material. It's not quite, but it's pretty similar to that. So this reaction zone, that wave that travels through, if you're really solving this problem, you do all the chemical kinetics, you'd solve all of those reactions. However, they're very fast, and that reaction zone is incredibly small for most products, or sorry, most explosives. Between the order of 0.1 millimeters and 0.05, so it's measured experimentally. And really, for the kinds of simulations that we run, which cities or at the very least rooms, it's just far too small to really have the effects that matter. So typically we make the engineering approximation that they're infinitely fast and they're zero length. It simplifies a lot and requires much less expense on the computational side. So the reactants, this is generally a solid phase, depending on the kind of reaction model you use. So we're talking about kind of a linear detonation model right now, but there are more complicated ones. You can have some equation of state for your solid reactants here. It's going to be the unreacted U. And basically that this reaction, the state, sorry, it's going to be defined by lambda here, which is basically reaction progress variable. So it takes a value between 0 and 1. At 0, it's totally unreacted. It's just that solid. At 1, it's going to be fully reacted. That's going to be the product state. And then each of these are going to be defined by a unique equation of state. So the products are where most of this happens. So this transition will typically milliseconds at the very most. Typically, it's much less than that, the time scale that these reactants are actually there. Usually it's just the very start of the simulation and then they're gone and then you're all product gases. So the product gases, we use a very weird equation of state for most things. So it's called the Jones-Wilkins-Lee equation of state, or the JWL. This is kind of the standard equation of state for high explosives. So you can see it's quite a bit longer than the standard ideal gas formulation. So we have this ideal term here, actually. So omega, which is essentially gamma minus 1. And then we have A, B, R1, and R2, which are all model coefficients. And this is kind of the non-ideal part. V here is going to be basically the density ratio between the solid state and the current state. And yeah, so this is going to be the equation of state that we use to define pressure and speed of sound and things like that for the reactor, sorry, for the products phases here. And then finally for the air, we just have a standard ideal gas. So you can, again, you can use any equation of state for this, for the kind of the model problem. Air burst, we're just going to be assuming ideal gas. Okay, so that linear wave speed is typically considered the linear detonation model. However, we do have some other models available. I'll actually be talking about one in a little bit. But basically we have a couple. So we have none, which is basically everything as soon as you start is detonated immediately. So you add energy at the start and that's it. You don't add any more. Next, we have the linear, which is what we just talked about. Then we have a pressure-based model, which basically uses the local pressure and density to define, give you some rate at which that reaction progress variable is changing. Radius rates are temperature-based, and then programmed ignition, which is a combination of the linear detonation model, as well as sort of a compressive activation model. And then we also have the option to include additional energy. These are typically called afterburn models. So we have Miller, which is going to be similar to the pressure-based, and then a linear release, which you do have to run experiments before. It's kind of just a matching tool. It's fairly common to be used, but these are typically used for internal detonations. And basically the point of these are to account for reactions that occur after that primary detonation event. So energy is still being added due to reactions, but it's not that primary detonation. So saw it kind of before with the pressure, but typically our blending between unreacted and reacted states are done in this manner here. So we have reaction progress variable to some exponent typically, which is 1, m, and then we have 1 minus that is our unreacted weight. And then we evolve lambda standard advection, and then we have a reaction rate as well. So R dot is really what changes here. So that's determined by whatever model you pick. And then we add energy based on the time rate of change of that reaction progress variable. And then we have E naught here, which is going to be the detonation energy. Typically, it's given in terms of a pressure, which is why it's over the reference density. And then we multiply it by our actual mass. And then afterburn will basically use this exact same equations. It'll just have a different reaction rate, a different activation energy. So both of the products and reactants are defined by a unique thermodynamic model. So like all OpenFOAM simulations, you have your transport, you have your energy, and you have your equation of state. So you need all three of those for both the reactants and products. So these are specifically the equations of state. There's nothing really different about the viscosity or the transport models or the energy models. So for the reactants, we have, so these are solid equations. So this is going to be Murnaghan, Birch-Murnaghan, second, third order, solid JWL, which is really the same as the JWL we talked about with basically a reference density. And then a Cochran-Shand model. And then for the products, the standard models are JWL, JWLC, which basically just drops the energy dependence and adds an additional offset. And then LSEK, which is similar to a power law. So these are kind of like the pre-compiled options, the standard options, if you will. But we do have basically any equation of state that we have, you can choose. It's just compiled at runtime. And then we have our activation models and afterburn models, which you have to choose as well. Okay, so now to some validation. So the Kingry-Bulmash, so these are basically simplified. It's a set of equations that are pretty standard for the industry being protective design. And these are really used to quickly determine blast loads on buildings and structures given a distance. So they assume a hemispherical surface detonation. And basically it allows you to find things like overpressure and impulse for both incident and reflected shocks. And then it also has a bunch of other things you can find, time of arrival, shock speed, negative phase overpressure, negative phase impulse, and then you also have positive and negative phase durations. All of these sets of equations all assume a TNT equivalence. So these were all done for TNT. And then basically, if you want to use something else like C4, you basically just have to convert that mass into an equivalent mass of TNT. So all the distances are scaled. Basically, you need to use the cube root of your weight distance divided by the cube root of your TNT mass. that'll give you your scaled distance. And then the results are in scaled units. So impulse needs to be scaled, time needs to be scaled, speed needs to be scaled, so on. So this case, we'll be using 10 kilograms of TNT. Our mesh domain will be 16 meters in length and height. And then our base mesh resolution will be 0.64 meters for the 2D case and 0.8 for the 3D. And then both of these will have 3 levels of refinement for the adaptive mesh refinement. So 0.08 or 0.1 meters. And then additionally, we refine our initial charge a little further. Basically, we just want to make sure that we get a correct and accurate initial mass of that charge. We don't want a super blocky charge, which is either going to overshoot or undershoot the actual mass that we're aiming for. So that's refined up to level 5, or sorry, level 6. Yeah, level 6 with adaptive mesh refinement. And then we don't actually use the detonation model, so this just means that all of that energy is added immediately. And then these are going to be our JWO coefficients. For anyone interested, so our code is available on GitHub, but these are all of these cases aside from the Pendine will be available in that. So there are actually 2 cases. So we run a 2D axisymmetric case. So this is going to be a wedge case. And we also run quarter symmetry. So here on the left, we have basically our axes. The bottom is going to be ground. And then the top and right sides are going to be outlets. So our initial charge is in that bottom left corner. So we'll show the plots in a second. So the main thing to make note of here is that quite different from like a standard set-off blast, which is basically just going to be an energy point source at the center, rather than having a nice smooth wave. Due to our equation of state, we actually get collapse and secondary waves. So you can see we have our primary shock wave on the outside, and then you actually have a second one kind of in the middle, and then you can see a pretty high negative or pretty low negative phase in front of that, as well as behind it, and then you get a smaller tertiary shock. So basically it just overexpands, collapses, get another detonation. And this is really due to that equation of state. And the bigger your charge, the bigger that effect. So here we have comparisons. So we have our maximum impulse, maximum overpressure, and then time of arrival, all versus distance. So the impulse is typically over-predicted for the Kingry-Bulmash equations. So it's pretty standard. Tim has actually written, I think it was a LinkedIn kind of article on this. But aside from that, the overpressures and time of arrivals all match very well. The 3 lines here are basically going to be ground plane, straight vertical, and then kind of a 45-degree angle out. Just different samples. And then next we have our quarter symmetry case. So ideally, this is exactly the same. Again, you see those 3 kind of those 3 shock waves, the primary, secondary, and tertiary. And then again, we have our plots. So we have slightly different impulse for that kind of 45-degree angle one. So that's going to be kind of a truly incident. And then we have everything else looks the same. Okay, so next we have a collection of rate sticks. So these rate sticks, the comparisons were made to Galicki 2007. And basically what we're going to be doing is we're going to be comparing the detonation velocities of RDX versus varying radii. So we have a 1D case, which is going to be an infinite radius, 20 millimeters, 12.5, 8, and 6. We're going to So the main point of this is to validate the pressure-based activation model. So we actually have a bunch of terms that can be used. We're going to be using one term from that. But this can also be called the JWL++ model. This is from Sowers. I don't remember the year. And basically the way that this is activated is it's hit from the bottom of the rate stick with some initial velocity. So here it's 90 meters per second. And we're going to be using a static mesh with a 2 millimeter mesh size. So the reaction rate used in the advancement of that reaction progress variable. So it's going to be some rate g times the pressure to some exponent, where P is going to be in megapascals, C is going to be 1 here, and then 1 minus lambda. And then the other difference between the standard model, so we're going to be using the Murnaghan equation of state. So this is just kind of a standard equation of state for solids. And then also we're going to be using that JWL-C term equation of state, which is just slightly modified from that standard JWL. So here we have our rate sticks. See if it loops. Good. So on the left, we're basically starting with an infinite radius, infinite radius, and then advancing smaller. So aside from the difference between 20 and 12.5, where the reaction takes a little bit longer, you can see that those wave propagations are slower as you move to the right. And this is really what we're looking for. So when we plot inverse radius versus detonation velocity, you can see that as that inverse radius increases, the detonation velocity goes down. And this matches very well with the original work of the implementation of the model from Galicki. And it does a decent job with Sowers, which is going to be experimental data. But this is probably mostly, the difference is mostly due to fitting of coefficients. Okay, so then the last case will be what we refer to as the Pendine case. So this Pendine case, we're going to take it from the work of Caitlin, 2003. And we're looking at an experiment conducted on the HSE blast range in Buxton, United Kingdom. So what we're looking at here is blast interactions with structures, specifically, non-standard structures. So it's not just reflecting off a wall. So here our charge is going to be 0.46 kilograms of PE4, and it will be top detonated. And then we're going to be looking at our overpressure gauges, which are 0.3 meters above the ground. So on the bottom here, you can see kind of the initial setup of the case. We have our explosive charge location, and then we have our 2 gauges located between the first and second and third cylinder or concrete obstructions. So this is actually just going to be an axisymmetric case. So we're not looking at 3D effects. We basically want those volume effects to make sure that we're correctly dissipating energy. But we're not actually, we don't really care about 3D effects for this case. So we're really only looking at that radial pressure movement. This is going to be the standard JWL equation of state. We're using a linear detonation model. And as I said, we're detonating this from the top point of the charge. So rather than the center, it'll be the top. Our base cell size is going to be 25 millimeters. Our max AMR level is going to be 3 or about 3 millimeters. And then our charge size is going to be 0.78 or 0.77 millimeters or level 5. So here are JWL coefficients. And then here are some videos of that. So the top, we have our pressure. Bottom, we have our density. So this was a pretty resolved case. Yeah, you can see kind of those vortices that have formed, the really low pressure dots. And then the black dots there are going to be our gauge locations. And then lastly, we have our Schlieren plots. So these are basically just density gradient contours, so you can watch a little bit easier how the actual shocks move. And then finally, we have our 2 gauge time histories. So these are really what we care about. They're just pretty pictures. So we want to see that these actually match. So the solid lines are going to be our overpressures. So green lines are BlastFoam, purple lines are going to be the experimental data. And then the dashed lines are going to be impulse. So you can see we match quite well. We at least qualitatively hit all of the peaks and valleys. Yeah. Quick summary. So we went over the governing equations. We saw some standard models for detonation, being the JWL linear detonation model, kind of that blending method. And then we saw the validation to the Kingry-Bulmash equations, the rate sticks, and then kind of that shock interactions with obstacles. So BlastFoam, publicly available. You can get it now if you want. So it's available on GitHub under Synthetik Technologies. So if you're using it, want help on something, my recommendation is always first go to the user guide. I think I have everything in there. I've really tried to include all of the model options, the basic equations as to how they're solved. There's not a ton on the theory, but there's some kind of basic stuff in there. But really, it'll give you all of the options which you can put, even if there's if there's defaults, how to override them, that kind of stuff. We have training if you're interested, private custom workshops. You can always email us at info@synthetiktechnologies.com. Bugs, you can always submit them to our GitHub page. You can email us too. And then if you're interested in something new, physics, models, whatever, we're always looking for stuff. So you can either email us or email us. And then references. And yeah, questions.
Very wonderful work and a very nice talk. So okay, it's time for questions. So are there any questions from our audience? For the attendees, yeah, you can write down the questions in the chat, and I will read on behalf of you, or you can unmute yourself and ask question directly. Okay, Jeff, maybe I ask question first. For your problem studies, I noticed that the domain, the computational domain is very large. And sometimes you use AMR to reduce the computational meshes. So my question is about the scalability of the BlastFoam when you use AMR. Have you tested that?
So as far as process count and stuff like that?
The question is scalability. So I mean, if you use more CPU, so the efficiency of the BlastFoam, yeah.
Yeah, so we haven't done a ton of testing with it. So we do have dynamic load balancing on, which greatly helps that. The main bottleneck tends to be actually at the start of simulations when So basically it forces that all of the initial cells be together. So if you have 1 meter cells, but you're refining down to like 1 millimeter, all of those have to be together. But I mean, all of our cases, it scales decently well. Local machines, it can kind of start to peter out when you start getting up to the top of like the local CPU cell count or CPU count. But yeah, we haven't had any issues. I don't have any super robust answers for that though, unfortunately.
Okay, thank you for the answers. So we have got actually 3 or 4 questions. So the first question is, can you talk about something about the numerical discretization schemes and the self numbers and any TVD type methods or any front checking methods or the equation type formulations in the BlastFoam?
Yeah, so we also have some over in the questions too. I'll answer that one first though. So numerical discretization. So we've done a little bit of work with it. So we have all of the standard limited schemes from OpenFOAM. So limited Van Leer or linear Van Leer, Super B, all of those. We typically use min-mod or Van Leer. Again, haven't done a ton of investigation into that. CFL numbers, it's kind of just finding one that works. So at the start of the simulations, I mean, you go from 0 velocity and a relatively low speed of sound to basically a super high speed of sound. So basically, once you get past kind of that initial dumping of energy, it tends to be pretty stable. So we have SSP methods in there. That's Ruth Spear 2001, I think, is all of this is in the user guide too. But basically we have, so the standard RK2 SSP method, and then we also have some higher step counts. I never recommend going over a Courant number of 1, but technically they're stable up to either 2 or 3 Courant number. So typically we'll use a little bit higher stability just that way. In the event that you do happen to go slightly over 1, simulation doesn't crash immediately. But really, once you get kind of past that initial hard part, it tends to be okay. We do not have any front tracking methods. I don't know what the equation type formulations are. Yeah, but standard TDD. Okay, so
next question is from Professor Zhang. So, hi Jeff, your governing equation presented is for 2-phase flows. Is the volume fraction of solved from the governing equations or from summing the particle volume in each cell? And do you use Euler Lagrange methods for Euler methods?
Yeah, so this is much more along the lines of like a VOF type simulation. It's not, but it's more along those lines. It's that shared velocity and temperature. So we don't have any dryag or anything like that. It's just a mixture velocity. So it's just going to be volume fraction. We don't use Euler Lagrange. We do have the option to include it. So if you want to do like Lagrangian particles, you can do that. And we also do have an Euler method, Euler solver, BlastFoam. But those are both quite different than what we typically solve.
Okay, thank you very much, Jeff.
Yeah. Yes, I think the volume fraction alpha is for the reduced 5 equations for compressible 2-phase flows. So there's no Lagrange method here. Is that right? And
yeah,
also
so
this
we're not
is
looking
different
at like,
from the VOF methods.
Yeah, so the main difference between VOF is that we don't have a sharp interface. So we basically have 2 gases, so we don't really care if they diffuse into each other. unlike standard VOF, which does care. They want to keep that sharp. Done a little bit of work with adding some additional schemes if you do want that. Specifically for like underwater detonations, you do want a nice sharp interface. So we've done a little bit of work with that. Not super stable, but that'll also be there in the next release.
So maybe we move to next question. So the question is from Xiongbin Jia, and his question is, I have two small questions. So first is the movie of cylindrical detonation evolution. Could you give more information for the formation of a secondary shock?
Yeah,
Okay.
This is probably one of my favorite parts about detonations. I think it's super cool. So basically, my understanding of it is that it kind of extends itself, so it expands too fast, and then you get these really low pressure regions, which basically cause things to come back together. So you actually get velocity coming back towards the center of the charge, and then after everything comes, it compresses, and then you get a high pressure region again, and then it detonates again. So this is pretty specific to the equation of state. So before I actually started here, I was playing around with just like standard ideal gas. You don't get it. So if you look at, so we have a validation case called SETOV, which is basically this problem, except it uses an ideal gas equation of state. It has a high, I think it's pressure, energy, whatever, at the center, and it's allowed to expand. And basically you get a nice smooth wave that just travels outwards and it trails, and that's it. So this kind of collapsing and redetonating is really due to the equation of state. Let me.
Okay, I think the second question is about the AMR. So the question is, for cylindrical detonation simulation, fine mesh is needed for accurate prediction, and the big computational domain is also necessary, and this brings about the expensive cost. So the question is how to better balance them. Okay.
Yeah, so AMR is widely used by us. For that exact reason. So we've done a little bit of work with GPU codes. So for most GPU codes, you have to have a fully refined case. There's no adaptive mesh refinement. And you tend to have just an insane amount of cells that are like just required because you have to refine that stuff. The nice thing about BlastFoam is you can do that adaptive mesh refinement. So if you have, a 1 kilometer domain and your charge is going off, and it really is only going to be affecting a pretty small amount, and you can basically just watch that primary shock travel away. While you will get a lot of cells around that shock, relatively speaking, it's much smaller cell count than if you were to refine the whole thing. So we've done a lot of work with that. So we have dynamic load balancing. So if you have 90% of the work going on one processor, it'll distribute that as long as it can. Always working on that. There's occasionally some issues, but it's been incredibly stable for us in the past. Yeah, that has been a large part of what we've done because it is very important. Because otherwise they would take a very long time to run.
I think the load balance is very well developed in BlastFoam.
Yeah. We did some of that, but a lot of that work was originally done by that Rettenmeyer group. I'm trying to remember the name. Yeah.
Okay, thank you for the answer. So we move to next question. So next question is, will the BlastFoam consider the DDT in granular explosives in the future?
So I guess it depends on how complicated you want to get. So right now, we've actually done a lot of work with granular propellants. So that's actually been one of my big projects. And we do have some simple models in there now within BlastFoam for that. So we have reacting particle, basically diameter models. So basically it'll add mass to the domain. And you can do it that way, adds heat and energy. As far as like full reaction chemistry, no. Maybe in the future, but not. There are currently no plans for that. I had actually done a little bit of work with that in my PhD, kind of biomass pyrolysis stuff. But yeah, as of right now, no real plans to do that. We do have, again, kind of that simple model, if you will. And then you can always do, I believe we have full support for Lagrangian. So if there's some reacting Lagrangian models, you can do that with them. I believe. I haven't actually tested that.
I think you need to hire more people to focus on this.
I know.
And this platform can be extended to many kinds of researches and applications.
Yeah, as long as it's very transient, it's for the very transient problems.
Okay, the next question is from Jason and Professor Heylmun. Thanks for your great talk. My question is that does BlastFoam can deal with the situation mixtures contains more than two materials in the same grade, i.e. Such as reactant product and the air exists in the same grade at the same time. I think this is for the volume fraction alpha. Yes, if it can, how multi materials mix in BlastFoam?
Yes. So the one we kind of talked about, so you have three equations of state, but technically you have two phases. And the reactants and products for this, so like that solid and like JWL, those are kind of just lumped into one equation. So they're, say, a detonating phase. So basically it's one or the other, or it's some blended quantity of them, but it's the same phase. You can do more than two phases. We have a multi-phase model. And it's basically the same thing. The only real difference is that rather than only transporting one volume fraction, you have to transport them all. But yeah, we have, I think it's called two-charge detonation. There's a couple tutorials with multi-species or multi-phase stuff, more than two. Yeah.
Okay, let's move to next question. So next question is Dr. Jeff Heylmun. Thank you for your lecture. In the last test case, the pressure at the probes increased very fast, while the numerical results increase much slower. How to explain this issue?
If you are, so I assume, correct me if I'm wrong here. So the both solid lines are going to be the overpressures. And then the dotted lines are actually impulse. So we have overpressure and impulse.
It's different.
So yeah, they're different. Which is why, so the impulse tends to be slower. So it's basically just that integrated overpressure, which is why it does increase slower. So yeah, you can, the scale for impulse is on the right side. If I'm misunderstanding that question, please correct me. But yeah, so the green and purple are the ones that are compared. The dashed and solid lines are different quantities.
Okay, so I think we have the last question. So last question is from Dr. Shampong Lee. And he said that what a nice presentation. And the simulations you present are at large scales, and the detonation wave structure is not resolved. If we use blast reacting foam solver, which chemical reactions can be used. Is it possible to resolve the reaction from the structure?
So theoretically, yes. So technically you would need a solid equation of state, which I don't think OpenFOAM, off the top of my head, I don't think they have one. So you can obviously add some. You could probably have the Murnaghan or something like it. You could do Lagrangian particles as well. That would actually probably be the easiest. The main difficulty is going to be in time scale. So like our time scales start off at like e⁻⁸, and then they move on pretty quickly because we don't care about that stuff. So to actually get all, yes, it's possible. It would be very expensive. So typically we just use results from experimental data is basically what it ends up being. All of those JWL coefficients are super easy to find, and I believe you can actually just use Cheetah to get them. Pretty sure you can just plug in your species information and it'll just spit out your JWL coefficients. Because those, they sort of incorporate all that, sort of. Yeah, you certainly can, just would be expensive.
Yes, yeah. I think if you limit your computation domain to a very small scale, and you can use much more computational grids, and you can resolve the reaction from the structure. Actually, it's like a quantity DNS. So there is no problem to resolve the reaction from the structure. Maybe the question is about the chemical reactions. So if you want to resolve the structure, so the more detailed chemical reactions need to be used. So it's,
yeah, I mean, you can do everything you can do in like standard reacting foam. So there's no limitations on like, they call it the combustion model, but combustion model or like reaction types, there's no limitation.
Yes,
there,
yeah.
so.
Yes. So is there any more questions from our audience?
Professor Jin, I think we have one question from Professor Fitzner in the chat function.
Where?
In the chat.
That's been answered.
Yeah.
It has been answered. Yes.
Oh, that's been answered. Okay.
Yeah. So maybe I ask one more question. So, so I think the purpose for your development of BlastFoam is for industrial applications. So is there a plan to develop the user interface for the BlastFoam? Because it will be quite convenient for people in the industrial field to use it.
Yes. So we're sort of getting our feet wet with that at the moment. We have a specific use case right now that we're developing the GUI for. It won't be public, it's for a client. But we would like to in the future do it. There's we're a fairly small company. So getting, and each of us are pretty well worked. So it's mostly just a time thing. But we are starting that. It is something that we're well aware that people really want and would be very beneficial. We will eventually. So.
Okay. So I think there will be no more questions. So Professor Zhang, do you have any comments or want to say something?
No, I don't have any more comments. So Jeff, thank you very much for your very nice talk.
Thank you for having me.
Yeah, it is a very important development, for to use OpenFOAM model at the high speed flows. Okay. Yeah. Okay. Thank you very much. So let us actually open the camera to thank the speaker again. Okay, thank you.
Okay, thank you. Thank you, Jeff.
Okay, so thank you. Bye bye.
Bye bye.
Bye bye, and have a nice weekend.